really dangerous to rely purely on friction to be able to turn corners safely. If we have different weather conditions or, I don't know, a poorly made road surface or one that's worn down, it's not a safe thing to rely upon that. So how could we have another force pushing us towards the centre of the circle to keep us safely going round corners? Well, one thing we can do, it's called banking the track. So rather than having a car going along on a flat surface, what we could do is we could actually put the surface at an angle. Now, why is that helpful? Let's look at a cyclist in a velodrome. That's what this thingamajiggy is called. In a velodrome, let's assume just momentarily, this isn't true, but let's assume momentarily that this is a completely smooth surface. There's absolutely no friction acting at all. You might think, oh no, these people are not going to be able to turn the corner because friction means it's not going to be pulling them towards the centre. They're going to fly off the edge here. Well, that's not actually the case. Now, you might say, oh, but, if there's no friction, the tyres won't be able to move, to turn, to be able to propel the cyclist forward. That's mere details in this scenario. So, let's look at the forces that are acting. Let's just look on the front tyre. We won't try and draw it on the back tyre here. But we're going to have a normal force acting perpendicularly to the surface here. And as we are used to, we're going to have a force due to gravity acting downwards. Now make sure you draw this in pencil because I'll show you I might need to adjust the size of these forces in a moment. So let's draw a free body diagram. That's just when you have a dot and you're just drawing arrows on it and you're not having to think carefully about where the force is being applied. You might find this really useful in those rough drawing force diagrams that we've talked about. Ones that aren't one of those draw the forces that are acting at the point of application, one that you're just using to visualize the situation. So let's draw these forces here. We've got a force due to gravity acting downwards. Yeah, I'm going to have to draw this one shorter. You'll see why in a moment. I think that's probably better. And we have this normal force acting at this angle. This may look, on the surface, particularly with this drawing here, like a ramp example or an inclined plane. But that's not the case because that's when we had an object sliding up or down or remaining stationary on a plane. This is a more two-dimensional, or I should say three-dimensional situation where this cyclist is actually coming out of the page at us. If I had to show the direction of the velocity, I'd do a dot out of the page. So this person's coming out of the page. We're going to be thinking of breaking up our forces horizontally and vertically just like we normally would. So I'm going to make a note here that we're going to be doing that just so you don't get these confused with a inclined plane example. So there we go. We're going to be breaking up forces horizontally and vertically. So let's do that in this scenario here and you'll see why this is so helpful. So mg is currently acting perfectly vertically so we can leave that alone. But the normal force, I might need to redraw the normal force, is going to be acting like this. I'm going to be drawing it slightly bigger in this direction. That's okay, you're all drawing in pencil, so I don't feel bad. There we go. So, what effectively is happening here? The normal force is made up of two component forces. We have this force that's acting vertically. Oh, now I need to redraw my mg. And that vertical component is going to be exactly equal to mg here. This component of the normal force is what's counteracting mg. So it's preventing the cyclist from falling into the surface or accelerating off the surface. That must mean that there is an unbalanced part of the force. This bit here. This component of the normal force, it is what is providing the centripetal acceleration. Sorry, centripetal force and acceleration. What I said wasn't incorrect, but it's what I actually, not what I intended. So this component of the normal force is our centripetal force. So in this example, the horizontal component of the normal force provides an additional, or in this case, the only, centripetal force. Let's look at an example of this. Here we've got a really hectic bus. We're told it's a Mercedes-Benz, it's a special test track. We're told the length of the coach, which actually is a piece of information we don't need for this question, but I just like that it's a real life situation, and that bus looks really crazy. It's not stationary there, it is travelling very quickly around a corner. It's relatively compact and it has short overhangs, and it allows it to traverse the sharp bank corner at 100 kilometres an hour. That's nuts. Now let's pretend the track is covered in slippery ice. This means there's no friction to provide a centripetal force. Remember, centripetal just means pointing towards the centre, so friction is not going to be a force pointing this towards the centre, allowing it to travel in a circle. We're asked, what is the maximum banking angle so the bus can safely make it around the bend? Now, I recall for this question I wasn't able to find the radius of the track. So I'm going to say, let's call it 25 metres. I'm not actually certain. So let's look at the forces acting on the bus. We've got mg that's just hanging out doing its own thing at a very funny angle here, and I might find it useful to draw myself a bus here. Again, this is not an inclined plane example. On an inclined plane, we talk about something staying stationary or moving up or down the plane. Not the case here. This bus would be coming out of the page. Now, we're going to have a normal force. I'm just going to be drawing the forces acting on this dot here. Let's just do a free body diagram. Now, this component of the normal is going to have to be the same length as mg, so I'm going to adjust that. That's the same. And this component of the normal is going to be what's providing that centripetal force. So the banking angle, we call this, is equal to the angle that I've drawn in here. It says, what's the maximum banking angle? There's two equations that we can do here. We can do sum of the forces equals 0 vertically. And before we do that, let's just write in, here we've got theta. This is the adjacent side, so this vector is going to be Fn cos theta. We don't know what the angle is, that's what we're finding in the question. And this being the opposite side is going to be Fn sine theta. Let's make a sign convention. I'm going to make up, and towards the centre of the circle I've got to make positive. That's the direction of acceleration. So I've made the upwards direction positive, and I've made to the left positive, because that's the centre of our circle here. You could have gone ahead and written Fn cos theta minus mg equals 0, or if you're more than comfortable to do this with Newton's first law, you could have just gone ahead and said, I know that Fn cos theta needs to balance out mg. Then sum of the forces is going to be mv squared over r horizontally, because we're dealing with unbalanced forces and it's an object travelling in a circle. So that means that Fn sine theta has got to equal mv squared over r. Now we're in a little bit of a pickle. We've got two unknowns, Fn and theta. But we have two equations, and you're probably familiar with maths. If you've got two unknowns and two equations, you can do stuff with this. We're going to be doing a little bit of simultaneous equations, so let's label equation 1 and equation 2. Now, let's do equation 2 divided by equation 1. My apologies if there's a change in the sound, I had to record this the next day. So we were setting up these equations here, and I said let's do equation 2 divided by equation 1. You could have done the reciprocal of this, but I know what we're sort of heading towards, and this will give us the nicest value later on. So to be able to do this, first off we need to divide the left-hand side of equation 2 by the left-hand side of equation 1. So what's that going to look like? We're going to have Fn sine theta over Fn cos theta. And now we're going to do the right-hand side of equation 2 divided by the right-hand side of equation 1. So it's going to be mv squared over r divided by mg. We've now got a little bit of double-decker fraction action. So just to review what we would do here, if we've got mv squared over r divided by mg, that's the same as having mv squared over r times 1 over mg. Hopefully you can see that we could cancel off these m's now, so the end result will be v squared over gr. Just wrote that alphabetically. Okay, so that means we're going to have v squared over gr. And on the other side, you might have noticed that we can actually cancel off these fn's. That's brilliant, because it means it's gotten rid of one of our unknowns. But we've got the issue that we've got a sine theta and a cos theta. We've got two separate thetas here.
Well, in mathematics, in trigonometry specifically, sine theta over cos theta, we're told that that equals tan theta. Brilliant. So this is a wonderful shortcut that I want you to have on your note sheets. We're going to review what to put on later, but this is what you're going to be using for banked curves. Now, specifically for this question, it asked about the angle, so we need to do theta, and that means we need to do inverse tan of v squared over gr. Haven't given us much room here, sorry. So inverse tan, the velocity that they've given us is 100 kilometers an hour. And to go from kilometers an hour to meters per second, we can divide by 3.6. So let's do that. We'll put in brackets squared. And we need to divide by gr, so 9.8 times the radius we said was 25. And popping that into my calculator, making sure I'm in degrees, I get 72. That's a huge angle. That's crazy. Now, the next example may not look like a banked curve kind of situation, but it uses a lot of the same principles that we just spoke about there. So I've gone ahead and labeled things on my diagram. We've got the force due to gravity, mg, is always acting downwards, and we've got the tension force acting here. It's really important to know that the length of the string does not dictate how large that tension force is. So this tension force, we can break it up into a vertical component, Ft sine 45, this angle here is 45, and Ft cos 45. Brilliant. So when we set up our first set of diagrams, first set of sum of the forces, if we want to calculate the tension, we could do sum of the forces equals 0 vertically. Rearranging this, well actually no, going back a step, if we substitute in, the vertical forces acting, we've got the Ft sine 45. Remember, you can use the ruler trick here to sort of scan along, there we go, to find the vertical forces. So we've got Ft sine 45 is acting upwards and mg is acting downwards. I'm not sure if I've mentioned the sign convention, but I'm making upwards positive because vertically it doesn't matter because we're going to be balanced, but I need to make towards the center of the circle positive. So substituting in our forces, we've got Ft sine 45 is balanced out by mg. Rearranging, Ft is going to be mg on sine 45. You might have drawn your triangle around differently to have angles here. The components here, I should say. You'll still get the same answer, even if your working out might look a bit different. So the mass is 0.10 kilograms. We're using g equals 10 for this question because it's listed at the top here. So it might feel a little bit strange, but hey, we've got to use the number of sig figs that they give us. And popping that into my calculator, I get 1.4 newtons. I'm going to need the entirety of that value a little later on. So please make sure that you keep that in your calculator. So to find the speed of the mass, we're going to use sum of the forces equals mv squared over r, and that's going to be horizontally. Horizontally, we had Ft cos 45, and that's going to be equal to mv squared over r. In order to find v, we're going to rearrange this algebraically. So we're going to multiply Ft cos 45 times r. We're going to divide it by m, and then we're going to take the square root. And as I've talked about in physics, every time you take a square root, you need to consider is it positive or is it negative. So for this, it's going to be positive. We're just interested in the speed, which is a scalar. So we're now substituting in the tension force. We've got the whole value on our calculator still. And we've got the cos 45, but we don't have the radius. Now, they strangely gave us the length of the string here, and that's the hypotenuse of a triangle here. So to find the radius of the circular orbit, that radius is this length here. That's the adjacent side on our triangle. So that's going to be 3.5 cos 45. Don't confuse this with the forces we just did. This is the lengths of the triangle. So that's why for the radius here, we've got 3.5 cos 45. And we're substituting in the mass, 0.10 kilograms. Popping that into your calculator, rounding it to 2 sig figs, I get 5.0 meters per second. So as a reminder, when we're doing banking questions, we are always going to have a situation where something's got gravity acting on it. And we're going to have some force, it could be tension, it could be the normal force, that's acting at an angle here. So we've got some object, and it's at some angle here. We are going to always break our forces up into horizontal and vertical, and this angle here equals the banking angle. Now, there are a few rearrangements that you might find useful to put on your sheet. The bare minimum, I need you to put tan theta is v squared over r. And you can rearrange that for v or r or theta, dependent on the question. You're not going to rearrange it for g, whoops, which nearly didn't get put in there. So the rearrangement for v, you're probably going to be taking the positive square root because you're going to be asked for the speed. So that's going to be gr tan theta. We multiply gr over to the other side and we took the square root. If you're finding r, that would be v squared over g tan theta. And like we saw before, if we were finding theta, we had to do inverse tan of v squared over gr. These are some really useful rearrangements. At the bare minimum, I want you to have this one here if you're really confident algebraically and you'd prefer to save that room on your note sheet for something else. I do need you to remind yourselves that we're breaking things up vertically and horizontally, not parallel and perpendicular to the plane as we did in inclined plane examples. Okay, you now have the knowledge to do the following, the 5.3 questions that I've listed below. Good luck and let me know if you have any questions.